All right. So how can we come up with some systematic procedure to select variables for linear regression? So recall that in linear regression, what we have is, so we try to estimate our y in the form of beta 0 plus beta 1 x1 plus beta 2 x2 plus and so on plus beta p xp, right? So p is the number of variables, but what if p is large? So what's going to happen? For instance, if p is bigger than the number of observations, our linear regression is not going to work at all, right? So, and even if p is not very big, like I don't know, so if you ever tried looking at statistical significance of coefficients of linear regression, right? So if I don't know, if p is, well, a reasonably large number like 50, when n is, I don't know, something like 1000, you probably know that usually all these coefficients are not statistically significant. So, and it looks a bit, I mean, picking all the variables, selecting all the variables to appear in the model doesn't really make a lot of sense. At the same time, it's hard to interpret such a model because of I don't know, there are just too many variables, and because it's too complex, and because there are probably multi-collinear predictors and so on and so forth, right? So what we really want is, out of a lot of variables, so if you say we have x1, x2, x3, x4, x5, whatever, x6, a lot of them, so maybe we can choose to just some of them that will appear in the final model. So how do we do that? And the best subset selection is just a procedure where we just compare all possible subsets of the model, right? So, and you know that if we have p predictors, right, so then the number of subsets of a p element set is 2 to the p, right? So basically we need to check all the 2 to the p subsets. So we're going to use this credit card data set. So the response variable is balance. So I have renamed it into y for convenience. So y is always going to mean the response variable in this lecture. So there are, in this case, there are 10 predictors. So the total number of possible possible models is going to be 2 to the power of 10, so which is 1024. So the best subset selection procedure goes like this, right? So for every value of k from 1 to, actually from 0 to k, so actually even from, we can start from 0. We do not have to start with 1. So we can fit all p choose k models, right? So we choose k out of all the p predictors, right? So the number of combinations is going to be p choose k, so the binomial coefficient. So this is p factorial over k factorial times p minus k factorial. And among them, we're going to pick just the one that has the smallest mean squared error, or which is the same thing as the residual sum of squares. And we're going to call it mk, right? So mk is the model with k predictors out of p that has the smallest mean squared error. But then we want to compare m0, m1, and so on up to mp, right? So we need to compare them based on some criterion that balances accuracy with the number of predictors. Because if we just compare directly m0 with m3 with m5, then of course m5 is going to be more accurate. But we need to kind of choose some other way to compare them. So there are various criteria. So among these criteria, so cross-validation error is something familiar that we learned last week. So this is from lecture 3. Adjusted R-square is something that you should have learned in regression analysis. And these CP, AIC, and BIC, I'm not sure if you have ever heard about them in regression analysis or in other courses. So I'm going to just mention them, but they're not going to appear in the tests. So it's just for your information, right? So here in this picture, every point is one model. Yeah, I did not show the model with 0 predictors here. So the total number of models here, the total number of points is 1023, right? And for each of these models, I just pick the best one, so the one that has the smallest mean squared error, and I just join them by a red line. And what you see that this red line goes further and further down. So with more predictors, the raw mean squared error is always going to go down, right? So which is why I cannot just use the raw mean squared error as my criterion, because then it will always select the model with all the variables as predictors, right? So then I have computed all these criteria. So CP, AIC, BIC. I'm going to tell what they are a bit later. So this is 1 minus adjusted R squared. So adjusted R squared. Now, so notice that cross-validation error and this CP, AIC, BIC, and so on. So big number means it's a bad model, right? So we want to minimize these criteria. While for adjusted R squared is the contrary, right? So the bigger it is, the better, right? So it's just so that we always have to minimize. I changed it to 1 minus adjusted R squared, just for convenience, right? And here are the plots. So these are the 4 plots with the 4 criteria, except for the cross-validation error. And I selected this the model that minimizes the respective criterion. So the value of k is slightly different, so it could be 6, or it could be 4 for BIC, or it could be 6 for the rest of them. So notice that starting from k, when k is 4 and bigger, these criteria do not really are not very powerful, right? So they do not really distinguish much so between different values of k. So probably this BIC criterion is probably the most powerful in the sense that it goes down and then visibly goes up again, right? So and when k equals 4 is the most strict minimum. So probably for this data set, BIC is kind of probably more powerful, and it is probably better. But in any case, so these are the definitions of these criteria. So Mellow's CP. So to find this Mellow's CP, we need to know the estimate of the variance of the error of our model. So we need to know this D is the total number of parameters of the degrees of freedom in the model. So this is just my mean squared error. So, and then we can calculate it. So I did not calculate it by hand, of course. In R, there is just a function for that. So Akai-K information criteria is completely different. So it also has this D, but also it has this maximal value of the likelihood function. So as long as we have some likelihood function that I don't really want to dig into. So if you're interested, you just Google it. I'm pretty sure that you had this likelihood function in your regression analysis. So I'm not going to bore you with details. So CP and AIC are very often equivalent, but so AIC can be applied for nonlinear models, I guess, as long as we can come up with some reasonable notion of what the number of parameters is. So this is BIC, Bayesian information criterion, and again we have this D, we have logarithm of the likelihood function, and this is the adjusted R squared. So in all these criteria, so we need to know, sometimes we need to know this likelihood function, so we always need to know the number of degrees of freedom right? So for in future, we're going to see models where this notion of the degrees of freedom just does not make sense. So the models are non-parametric. So there is no such thing as the number of parameters. So for them, these four criteria, of course, cannot be applied, right? So and you don't need to remember these definitions. So they are just for your information. So if you're interested, you can dig deeper for your course project. So you can, I don't know, make it as a part of material beyond the course syllabus that you're going to exhibit in your course project. So in practice, you can always use the cross-validation error for each game. And this is something familiar. So you can compare different linear models with different numbers of variables using the cross-validation error. Okay, so that's the end of part 3.